discuss in compressible flow. And also, we have a circulation of this fundamental equation, that is Navier-Stokes equation. The video part of, the pre-recorded, there is no pre-recorded lecture on that particular Navier-Stokes equation. Since that part is not explicitly in our syllabus, although we use it because at times Navier-Stokes equations can be handy to use in different problems. So that's why actually we have circulated you the derivation, the equation, the note actually, so where you can, I think if you go through it, you can understand how the constitutive equation in 3D Cartesian reference frame, we can able to arrive in that form. Now there are two different approaches for handling these fluid mechanics problems. One is direct use of these Navier-Stokes equations, but Navier-Stokes equation itself is having some kind of its own assumptions. You cannot use Navier-Stokes equations in any type of situation. And the other approach is typically the one you handled in your fluid mechanics course, fluid mechanics 1 course. That is what we call as the control volume approach, in which you considered control volume, which is fixed in space. And then with certain assumptions, applying the fundamental principles, we arrive in certain equations to relate the phenomena which you are going to study. So that is the general approach, we can say. When you have derived this, for example, Euler equation or Bernoulli's equation, and later the Zagan-Poiseuille equation, you can recall that in all the situations, the approach was to construct an infinitesimal volume in space, and then considering the different situations. At times we neglected the effect of viscosity. At times we considered the effect of viscosity, and so on and so forth. So like that. So that was the treatment typically we had in fluid dynamics part. In your fluid statics, we had a separate approach. And of course, you had a little bit of kinematics, fluid kinematics part also, isn't it? So in your fluid mechanics 1, typically there are three parts, fluid statics, fluid kinematics, and fluid dynamics. A little bit of fluid dynamics was also there. What else? Can anybody remember?
Fluid machinery.
Apart from the statics, dynamics, and kinematics in your fluid mechanics 1, any other thing that I have missed? You can help me out.
Viscous flow, pipe networks.
Moody's diagram গুলো ছিল
ওটাই তো পাইপ নেটওয়ার্ক গুলো
Just a minute. When you... Yeah, my speaker volume was muted. So can you please repeat? Some students responded, but
yes,
unfortunately,
sir.
Yeah.
Pipe network, Moody's diagram, friction factor.
Right. 5 net. So typically
Actually,
those,
viscous flow, sir.
yes, of course, viscous flow
Free
and
surface flow.
free surface flow. Okay. Yeah, the or open channel flow or free surface flow. Correct. So viscous flow or this five network, what you were saying, that is typically the what we call as the pipe flow, in which typically the Eigenpoisson equation we came across, then your Darcy's equation, the friction factor that we are talking about, and another aspect of fluid mechanics is of course free surface flow. Different applications you can see it in preparing or in designing the channels for this hydraulic power plants or irrigation. So all those channels are actually falls under the ambit of free surface flow or open channel flow. Right. So the thing is that in so in fluid mechanics was very interesting. I mean, we started with a situation where fluid is not moving, and that is what we call as fluid statics. And then we have the fluid considered to be a particle, like what you did in a solid mechanics course. And then the motion of the particles, like the solid mechanics or a solid body, considering to be a particle mass. But the problem with fluid mechanics or the fluid body, to consider a particle is not as straightforward as we can have in case of a solid body. Can anybody tell me why the problem is to consider a fluid, or why it is very difficult to monitor or to track a particular point mass or a particle in case of a fluid mechanics situation? Or if I put this particular question in a bit different way, the thing is same. If I want, I mean, more fundamental way is what is the difference between a fluid and a solid? This is the most fundamental.
Fluid cannot resist shear stress under static condition.
Fluid cannot resist shear stress under static condition.
But solid can, sir.
Yeah, so that is the most fundamental difference, solid can resist up to a certain limit. Okay. After that, it starts deforming. But in case of fluid, whatever be the magnitude of this tangential stress, it always starts deforming. So that is the main difference between solid and fluid, which composed of gas as well as liquid. So both are falls under the category of fluid. So due to this deformation, which is inevitable whenever there is a motion taking place, so it goes on deforming. So thereby, a particle approach is a little bit of a difficult task. So this particle tracking approach is what we call known as Lagrangian approach, and the other approach, the one which is typically being used in fluid mechanics problems, is known as the Eulerian approach, right? And from this particular Eulerian approach came the concept of control volume. That means a volume which is fixed in space. In case of solid mechanics, you can understand that where mass is fixed, okay, but in a control volume, we know that mass can enter, mass can leave across the control volume, as well as mass can accumulate within the volume. Right. There are other properties also which can interact with this control volume and surroundings. So, like energy, like momentum, and that is the starting point where we, using this approach, we arrived at the mass conservation equation, which in differential form, what is the name of the particular form of mass conservation equation in differential form? Apart from Bikram, others should also try to interact. Anybody else can able to tell me what is the name of that equation, which is a mass?
Reynolds transport theorem or what it was?
Euler
Not
equation.
not exactly Reynolds transport, not exactly Euler equation.
Continuity equation. Continuity equation.
Correct. It is basically the continuity equation. Continuity equation that is a mass. It came from mass conservation principle in its differential form. In a similar manner, we had the linear momentum principle that is just applying Newtonian principle or Newton's law of motion, the second law, from the same which we have in solid mechanics as well. Basically, there are very few number of natural laws available, typically for Newtonian mechanics, which is applicable for solid mechanics as well as fluid mechanics. Or in other way, we can say that we are confined ourselves within this Newtonian mechanics principle. We are not having other form of physics like quantum mechanics applied in this particular. Typically, engineering or mechanical engineering, for most of the problems, almost 95% problems can be solved using, at least till date, can be solved using this Newtonian mechanics principle. So we are fortunate in most of the situations we straight away go for this law of motion and conservation principles, which are very few. So you are having three laws of motion: first law, second law, third law, and you are having the conservation of mass, conservation of momentum, and conservation of energy. In fluid mechanics, we typically use this conservation of mass and momentum. And from momentum, actually, we can also arrive into a special case of energy equation, which you also did in your fluid mechanics 1. Can anybody tell me where actually, from momentum equation, you arrived at this energy equation? Can you recall?
So from Euler's equation along a streamline, we arrived at the Bernoulli's equation.
Okay. So Abhishek, is it Abhishek or I'm talking with Narendra Modi?
Sir Abhishek.
Okay, because your this picture is I was actually frightened that Narendra Modi was speaking with me. So it is better, I think, everybody to either change your profile picture so that I can see that they are students. Right. Of course, it is your choice, your own choice, but it is my suggestion. So yes, Abhishek, correctly you have said it is basically the Euler equation along a streamline. When it is being integrated, then we arrive to the equation which is, I think, mostly used or mostly known equation. Fluid mechanics means Bernoulli's equations. Many of the students, in 10, 20 years down the line, if you ask somebody what is fluid mechanics, it is Bernoulli's equation. The equation which is remembered, okay, for a long time. And that is basically sort of energy equation, which definitely certain conditions. So, and it actually it can be arrived at from two different approaches. In fluid mechanics, what we did is we started with momentum equation along a streamline, and then we arrived at Euler, what is known as Euler equation. And then we dropped certain term, further assuming steady condition and incompressible, so that you can able to integrate it very in a very straightforward manner to arrive at the energy equation, which is termed as Bernoulli's equation. So those are the things, I mean, which we can relate, and I can see that yes, you are having quite a good knowledge. I don't know, of course, but responses are good from you. Okay, so the thing is that whatever knowledge we gain in our fluid mechanics 1, we want to carry it forward to the next level, which is fluid mechanics 2. And in entire fluid mechanics 1, our approach was control volume, as I said. But in fluid mechanics 2, we will try to look into certain situations where you can have this Navier-Stokes equation, which is nothing but your momentum equation with certain assumptions. Okay, it is a three-dimensional flow, or it's basically representing a generic situation where you have the viscous effect, you have the surface forces in general, you can have the body forces, and of course the inertia terms in all three principal axes. So altogether, you will be having a stress tensor. Then there's accelerations, which you probably learn from your kinematics, fluid kinematics, and a little bit of viscosity, and you have learned in your fluid mechanics 1. I mean, it actually started probably with the discussion on the properties of fluids, and in which the most important property that we normally discussed in first level of fluid mechanics course is the viscosity. Because yes, somebody that correctly pointed out that deformation of fluid when it is in motion, it is actually that unique property which the moment fluid starts deforming, it actually offers resistance to the cause due to which it is deforming. Okay, so the property due to which it can able to resist is the viscosity, which do not exist in case of a solid. So that is one property which is unique to fluid. And due to that, we have the viscous shear stress. The relation between this shear stress, viscosity, and the rate of deformation, we learned in our fluid mechanics 1 in terms of what we call as another law. I mean, that was Newton's law of viscosity, and the fluids which obey this particular law, we call them as Newtonian fluids. I mean, that also means that not all the fluids in world are Newtonian. So there must be some other kind of fluids which do not obey this Newton's law of viscosity. So those are non-Newtonian fluids. Right. So so that particular Newton's law of viscosity is actually confined to a certain dimension of flow, whereas later actually Stokes' law of viscosity encompasses the more generic situation of viscous effect, so which is known as Stokes' law of viscosity. In this Navier-Stokes note, you can see it started with that Stokes' law of viscosity, and of course, I mean, if you impose those assumptions, you can always reach to Newton's law of viscosity from Stokes' law. So my point is that Stokes' law is not defying your Newton's law of viscosity. It remains still valid. And so that is why actually we, at the fundamental level, to understand in a better manner or for easy understanding, it is better to start with Newton's law of viscosity and later with handling of Stokes' law and thereby this surface force in terms of the shear stresses and considering the body forces also and this inertia force, you can frame complete equation of motion, which is known as Navier-Stokes equation. So the contributory part of Stokes is actually this viscosity law in these Navier-Stokes equations or in NS equations. So in further, we in our next topics, that is the first one already with you, you can see, I think you should have seen the first one that we dealt with was flow between two parallel plates, where the approach was using the Navier-Stokes equation straight away. Right. Okay, so and another, actually I'm trying to just summarize what you have learned and what are the connections with this Fluid Mechanics 2 course with Fluid Mechanics 1 to maintain here also, to maintain the continuity, right? So apart from this, in Fluid Mechanics 2, we will move on to certain aspects of fluid mechanics, which are more practical, so to say. And also, you can have a contrast, a more practical to much idealistic situation also we will deal in Fluid Mechanics 2. So our starting topic actually is viscous incompressible flow. That means we need to consider the effect of viscosity. But the flow will be incompressible. Incompressible means, what is incompressible flow? Anybody?
The Mach
Density
number
is
is
constant.
yes.
Yeah, anyone.
The Mach
Big
number is less than 0.3 or between 0.3 to 0.4.
Mach number.
Material
Yes,
density is constant within fluid.
So
In the
material
net.
density is less than, change in material density less than 5%.
Yes, sir. Yes. Density will not change.
Devjit, can you please come again? Material density less than 5%. The change of material density.
Yes, sir. Change in material density with respect to previous density is less than 5%.
Okay. So, Bikram, Mach number, in terms of Mach number, what you tried to say, I didn't get because I don't know what is Mach number. I know what is density right now. Mach number, I don't know whether in your Fluid Mechanics 1 course you have learned it or not. Maybe in your school level you have learned something on Mach number, that also I don't know. But it is more appropriate to define the incompressible flow is that change of density where can be neglected. That means with time or with space, because fluid mechanics domain is not confined in time. With space also, we by now you know that it is also very variable with respect to space. So we altogether require 4 dimensions to designate or to describe fluid mechanics problem domain. Isn't it? Either it could be, the spatial could be Cartesian, it could be cylindrical, it could be spherical. And of course, time is another independent variable. So incompressible flow is basically the flow where we can neglect the change of density. Or in other words, you have the fluid which is not being able to compress. That is why it is incompressible. So
Sir, can't we have a situation where the incompressible flow is going to have a varying density?
no, you are actually that is a self-contradictory statement because we are classifying the fluid mechanics situations in different domains which are not exactly the real situation. If you ask me, there is no fluid possible where the density change do not take place. All fluids, I mean, liquid particularly, apparently it seems that density changes are not there. But yes, of course, density do change, and but the term is negligible. The change, if it is negligible, then we can reasonably consider the fluid to behave like an incompressible fluid. This is basically for our ease of handling of certain situations, which is close to a real situation. Engineering is like that. I mean, that is the difference between engineering and physics. A physicist can go towards accurate solution. I mean, which may not be requirement, which may not be the requirement. Accurate means theoretically accurate. Okay, so that said, this negligible, but you can define as negligible. Somebody said if the change is within 5%, so that is more. I mean, that is a kind of definition where you are quantifying what exactly you mean to say as negligible. Okay, there is no fuzziness in this definition of say 5% or 1% or 2%. You are saying that if the change is within 1 or 2%, we can safely neglect that change. We can the change that may not be able to detect. But if you go for a theoretical analysis of that situation, you are having tools. You are having tools means you are having mathematics in your hand. Okay, you are a very good mathematician, so and you can apply those mathematical principles in any physics problem. You are applying it, and also nowadays you are having a huge facility of computational work. I mean, which you cannot able to do maybe with pen and paper in an analytical form. You can use those formulations to solve the situation in a mathematical manner using numerical techniques with a very say high power computational platform. And you find that yes, the density in the particular domain is changing, right? It is not incompressible. The consideration of incompressible is wrong. So you have come to that conclusion. Okay, so if it goes to an engineer, a situation where in a much lesser time, the solution has been done. It has been achieved. What to be done, considering incompressible flow. So, and one can see that it works nicely. It works fine. So no point in going into that kind of a very detailed analysis, which ultimately resulted 0.5 or 1% change in density. Okay, in real world, of course, if you go into that scale where maybe it matters, you need to consider. But in other situations where the scale on which you are working means the characteristics length or the size of the domain that you are considering within that domain and the magnitude of the parameters defining the situation, with respect to that, if the change is that level, it is better not to consider it to be changing. So, in lieu of that, actually, what we get a very handy form of equation which can be solved very conveniently without going into that complicated or much tedious numerical handling. That is the objective actually. And till now, I mean, most of the engineering problems have been approached in that manner. But of course, I mean, there are scopes of changing the situations using the infrastructure nowadays, what we are having in terms of computational platforms, and also the different softwares, which also gives us so many avenues which otherwise were closed, okay, because of non-availability of these facilities. Okay, so nowadays this design, etc., are becoming more and more elegant. And one can previously, when design were made, so many over-designed situations were there, and that actually led to, say, for example, while designing, if you consider an ambassador, I don't know whether all of you have seen an ambassador car or not, because nowadays it is almost verge of extinction. Typically, some taxis are there in Kolkata plying. Those are the ambassador Hindustan Motor Car, and it was actually over-designed vehicle. And also we can see other types of cars which are plying, and more sophisticated techniques nowadays are evolving to design those cars so that it actually gives you fuel efficiency. That is the most important consideration. So, I mean, how this evolution took place? I mean, from this towards form of calculation, towards form of approach to final form, of course, with the help of tools like this computational platform and softwares, we can able to reach to this particular world where design no longer are being done using only pen and paper. And that lead to so many, I mean, you can have material reduction that will lead to lighter weight of, but also it is, its strength point of view, it is tougher. And also more lighter the vehicle, more aerodynamic shape will give you less amount of drag, and thereby you need to have less fuel consumption. Okay, so that is the way. So coming back into our particular discussion of this compressible or incompressible, the thing is like that. You need to consider, I mean, you have to decide. I mean, it is basically the engineer or the analysts who are doing this particular problem-solving job or for a design job. So whether to consider this certain changes or not, it is, of course, the prerogative of the design engineer, and with solid justification. Okay, otherwise people may not accept it. People means I'm talking about time, and thereafter it may go for production. So in order to establish your case, you need to have solid ground. Okay, so that is the point. I mean, whether it is to be considered incompressible or compressible. The reason behind having this incompressible flow study is that you can have Bernoulli's equation in your hand. One very common example. If you do not consider the flow to be incompressible, you cannot use Bernoulli's equation. You cannot integrate Euler equation in that straightforward manner. All right. So, but Bernoulli's equation works nicely in so many situations, considering certain other parameters. I mean, a modified Bernoulli's equation, where people, I think, I don't know. Yes, of course, you have probably used that, no? Modified Bernoulli's equation. Where you have used, can you remember? Have you used it? in fluid mechanics one? Modified.
Yes, considering the
লসেস গুলো যখন অ্যাকাউন্টে
Right. While considering the losses, major loss or minor losses,
Yes, sir.
basically Bernoulli's equation is a balance sheet of energy. It's a kind of a debit credit statement of energy. Left hand side and right hand side you need to match so that the total energy remains same. Right. It's a commerce kind of a thing. So, but in ideal situation, our total energy line remains same, isn't it? So if you move from point 1 to point 2, point 3, a different point or a cross section in the direction of flow, you need to have the total energy count to remain same in ideal situation. But in real situation, you have losses, which is irreversible. So the total energy actually goes down. So if you then consider that particular losses into account, then your balance sheet will once again gives you very nice matching. The left hand side and right hand side will become same. So the total energy once again is preserved. That form is known as modified Bernoulli's equation. Okay, so this viscous incompressible flow is a kind of situation which you may encounter in certain fluid mechanics flow problems. For example, this flow between two parallel plates which are separated by a certain distance within which the effect of viscosity cannot be neglected. Right. So that is the important point here. The effect of viscosity cannot be neglected in certain distance between the two boundaries. Okay. That means, say, if you are having a duct of 1 meter square cross section, then it is actually not prudent to consider the effect of viscosity throughout the flow regime within that particular cross section. It can be seen that the effect of viscosity is prominent near the boundary. Okay, near the boundary means the solid boundary through which fluid cannot penetrate. But away from the boundary, after a certain distance, we generally don't have the effect of viscosity. Again, that is relative. In terms of the percentage that in case of compressible, incompressible flow you mentioned. So definitely there will be effect of viscosity. But if it becomes, say, 0.1% or 0.01%, again, we can neglect that effect and consider the flow to be free of any viscous effect, what we call the single word as inviscid flow. Okay, invisid flow, yes.
আপনি কি স্ক্রিন শেয়ার করছেন?
না, কোনো বন্ধ করেনি।
আচ্ছা আচ্ছা।
So I'm just actually having the entire fluid mechanics, whatever you have learned and what we are going to learn, to have a connectivity, to establish a certain connectivity from your previous knowledge. So these also you have done. In the first part, the moment you understood the property of viscosity, then came the fluid statics. Probably that was the sequence, isn't it? After the property, it came the fluid statics, where fluid is in static condition, so there is no question of any viscosity. Because the effect of viscosity was felt when fluid is in motion. When it is not in motion, there is no effect of viscosity. So viscosity gone when you learn the statics, right? In fluid statics, can anybody cite any situation where you have the effect of viscosity or the kind of viscosity was considered? Anybody? I believe no, nobody, because there was no no word of viscosity in the entire fluid statics chapter in any book. And then we went into that acceleration. I mean, the kinematics, fluid kinematics. There also there was no such viscosity. And when we started fluid dynamics, we actually considered the fluid to be ideal. Ideal means it is inviscid, incompressible, both, isn't it? So when we consider the flow to be inviscid and incompressible, that means there is no viscosity, no change of density. So again, we came back into that viscous effect when you went into pipe flow, that Hagen-Poiseuille equation, or before that, probably you have learned something about the kind of flow, laminar, turbulent, etc., and the transition flow, Reynolds experiment, kind of Reynolds apparatus, Reynolds number, right? And then typically the pipe flow, and in case of laminar fully developed flow, considering in the control volume, while deriving the pipe flow equation, if you can recall, you had the tangential stress acting. Why you considered that? Because the effect of viscosity can be felt there. Right. So and that actually is near the boundary wall. If you have the velocity gradient, that del u del y or du dy in case of 1D flow, one-dimensional flow. So where actually this du dy term going to be maximum? Is it at the center of your flow geometry or at the boundary?
Boundary, sir.
At the boundary, because it is at the boundary you had from the Newton's viscosity, law of viscosity, we have tau is equal to mu du dy or del u del y. So if this term del u del y is maximum, and you have a viscosity which is constant, for Newtonian fluid, of course, it is constant. So if I have this gradient maximum, I can have the corresponding stress to be maximum. So at the boundary, we have the maximum shear stress. Boundary means the solid boundary I'm talking about. So as you go on away from the boundary, this gradient goes on decreasing, and somewhere at a particular distance away from the boundary, that rigid boundary, that del u del y or the gradient may become almost zero, nearly equals to zero. Theoretically, it is not absolutely zero, it is not possible, but it is close to zero, maybe say 0.01% of the maximum value. So that point onwards, if you move on further away from the boundary, it can only decrease. I mean, this gradient can only decrease. It cannot increase, because as the effect of viscosity is getting decreased as you go on away from the boundary. So if you have, say, 50%, for example, and just for example, say 50% of the dimension in that direction where you have variation of velocity, that means you are having some gradient in that direction, the length of, say, 100 centimeter length of the entire domain, out of which for the first 25 centimeter, again, this is just exaggerated value, you have the effect of viscosity. For the remaining 75%, there is no effect of, or nearly negligible effect of viscosity. Okay? So we can have two distinct regime of flow, considering effect of viscosity and considering no effect of viscosity. This no effect of viscosity it can be a significant flow regime. And that actually, the moment you have no viscous effect, if you can see the Navier-Stokes equation, there are quite a significant number of terms which are viscosity dependent terms. So all those terms can go. And some other treatment of the fluid mechanics problem is possible. The moment you consider the flow to be inviscid, the moment you consider the flow to be incompressible. So that entire domain of analysis is known as ideal flow analysis or potential flow theory, which we will going to visit in our fluid mechanics too. Although it is ideal flow, it finds application. I mean, it gives certain clue towards real problem solution, okay, or we can say real world problem solution, right? So that is why even if we are calling it as ideal flow, it finds significance still now. So that will be our another important topic after this viscous incompressible flow. And so, as I said, two distinct regimes can be thought of. One where the effect of viscosity, effect of density may be neglected. And the other regime, of course, can be where you are having effect of viscosity significant, effect of density change can also be there. We can further, have the classification, means where the regime where we have incompressible situation, but the effect of viscosity is there. That is the viscous incompressible flow, which we are right now going through, right? Another area related to this, where you can also have the effect of this density change possible, and it is very close to the boundary, that regime which we call as boundary layer flow. That means the treatment of flow in the proximity of solid boundary gives us, in fluid mechanics, gives us a significant or a revolutionary change in terms of designing the surface of different vehicles or different moving devices, starting from underwater to aircraft or surface vehicles. The knowledge of this boundary layer, which is more recent, you can say, in terms of the evolution of fluid mechanics, which is known as boundary layer theory. So after this knowledge, actually the designing of the surfaces of these vehicles which are having interaction of fluid, be it underwater or aerial or surface, whatever. So that is another area which we need to have a visit in our fluid mechanics too. Of course, in a basic level, because boundary layer theory, more in-depth study calls for post-graduation level course. Okay, but we will have a visit on this boundary layer flow theory. And then comes another area where up till this boundary layer flow, we can have the effect of density not to be considered, but there are a domain, particularly in case of aerial vehicles or aerospace applications, where a change of density is inevitable, because it is air now, and there will be change in temperature as you go on increasing your altitude. So you cannot now neglect the effect of this density. It will be more than 5%, right? So you have to consider. So that the moment you start considering the change of this density, now it is not incompressible, rather it will be compressible flow analysis. Okay, typically for aerial situation where you have this change of density taking place. So that compressible flow will be another our topic of study. We will visit again basic nature of this compressible flow, because all these are in undergraduate. All these are some basic inputs we will try to disseminate to you. If anybody is interested, he can have an entire course on compressible flow. He can have an entire course on boundary layer flow. So those are the avenues. Okay, so we are only going to let you know that these are different avenues through which you can move. You can move on in future. Okay, or you can do something if you want. And yeah, so the thing is that, so that is the compressible flow we will visit. And you know, in your again, let me go back to fluid mechanics 1, where the moment you derived Euler equation that using the principle of momentum conservation, then you drop the term unsteady term, right? If you can recall, considering the flow to be steady. And that point onwards, actually, I think you have not considered any situation where you have the time-dependent term to be present. Am I correct?
Yes, sir.
Yes, sir.
Yeah, so entire fluid mechanics 1, and also basically, I mean, in entire fluid mechanics 1, except the kinematics part, in fluid kinematics, maybe you are having some problem where your del U del T or del V del T or del W del T terms were there. Other than that, I mean, those are just for the sake of some numerical problems. Other than that, I believe nowhere in your fluid mechanics 1 you have any time-dependent term. Acceleration was there, but those were due to the spatial variation, not due to time variation. Right. And as you can see in fluid mechanics 2, till now, I mean, whatever you will go through, be it viscous incompressible flow or boundary layer flow or compressible flow, it will be dealt under steady state condition. That means we are not going to have any time dependent variables. Okay. But again, if you look into the real problem, real world situation, I mean, it is not that something is being changed instantaneously. That means you are having a certain equilibrium condition. You want to go to another equilibrium condition. It is not possible to go instantaneously from one equilibrium to another equilibrium. Always you require certain finite amount of time, right? So if you are having a vehicle, your car, if it is moving at a velocity of, say, 50 kilometers per hour, and if you press your accelerator further, you cannot expect to have the speed 80 kilometers per hour in no time. No time means no time, zero time. It is not possible, right? So you need to have a finite time for this change to take place. So whatever change is taking place before it reaches to a steady state, so to say, or an equilibrium. Equilibrium means with respect to time, I am talking about this equilibrium. It may not be the equilibrium with respect to space, but if you are looking for a time independent, that means no change with respect to time from one point to another. So that particular regime of analysis, where you have variation of the parameters, velocity or temperature or pressure, is changing with respect to time is what we call as unsteady flow. That means the flow is not steady. It is unsteady. And there are, again, as I said, just one example. Always in any problem, whatever you consider, if you consider incompressible, that means the moment you are considering incompressible, the consequence is that you do not have any kind of pressure transient. That means there is no dp/dt term that will exist because of this incompressible nature of flow. Because pressure and density, they are correlated, right? Because the moment you apply pressure, density needs to be changed. Otherwise, you cannot have the deformation possible. So it's a theoretical thing that you are changing pressure, but you are not having any kind of change in density. So, and that actually means that the change in pressure, this information, if you are having incompressible flow or an incompressible fluid, it will be transmitted in an instantaneous manner. Right. So this information actually, in real situation, it takes time. So if you want to find out how much time it will take and what is the behavior of this change of pressure, if you have a disturbance in the fluid, say for example, I don't know how many of you have experienced it. Say if you throw a pebble in a stagnant water, I say in a pond, what will happen? Yeah. Somebody wants to say something?
Has a repels over.
Ripples. Some kind of circular ring one can able to experience. It is actually originating from the point where your pebble is being immersed. That actually will act as the center, and taking that as a center, some circular ring type of wave, what we call, will start emanating, and it actually reaches to the bank. Okay, so that is basically a kind of disturbance that you impose to the otherwise stagnant water, and due to that disturbance is actually propagating, and it propagates in all directions. That is why you are having the circles. It signifies that disturbance is being propagating in all directions, right? So the information of that disturbance is being transmitted from the point of origin to the end, and the end is here, the boundary, that means the bank. Okay, and visibly you can see that it takes time. It is not going to be an instantaneous travel of the first circle from that place of immersion of your pebble to the place where you are standing. So that is what we call as the transmission of pressure wave, and that falls under the treatment of unsteady flow. So that particular area also another important area of fluid mechanics, and we will try to visit that also in our fluid mechanics too. So these are the broad topics of different fluid mechanics situations, which will be covered in your fluid mechanics too, with some few with another additional topic that is not exactly fluid mechanics. It's a kind of a tool which is known as dimensional analysis. So there is a kind of tool knowing which you can form certain groups to have some kind of correlations. Like for example, one group already you are aware of, you have done it, that is our Reynolds number, and with that friction factor, Reynolds number relation. Okay. So using this dimension analysis, you can also form certain dimensionless group, which from which you can correlate with some physical phenomena. Okay, so that technique we will just go through, and I don't think any kind of much discussion is required for that. I mean, material will be given to you. Again, if you need 1 hour duration is good enough for discussion on that. So this is all together, I can say, the overview of the course Fluid Mechanics 2 that we will be discussing, and we want to study in this particular semester. So already the material, the first material, that is Navier-Stokes equation and viscous incompressible flow part is given to you with the video also. So it is about 3:30 now, so we can have a 5 minutes break if you want, and then we can start the query part from your side. Whatever you have gone through, and let the first two topic, I mean, on viscous incompressible flow, that is flow through parallel plates and Helmholtz equation. That is actually the revisit of Helmholtz equation with a different approach. So if you want up to that any kind of discussion, we can do that in our second half, right? So if you want a 5 minutes break, we can have, or otherwise, if you want to continue, we can also continue. What do you want? Everybody is silent.
After 5 minutes.
So 5 minutes for a
5 minutes. अच्छा, ठीक है. So it is 3:34, 3:40. Okay. Okay. Okay.